Greetings, physicists. In this video, we're going to be talking about how to solve problems that involve stored energy or potential energy. And when I say stored energy, I mean not stored as motion, because you can sort of say that kinetic energy is storing energy as motion. So, first we'll start with some gravity stuff. We've got people, I guess this is a yearly thing. They do the Empire State Building run-up, and you start at the bottom, and you run up like a lot of flights of stairs to get to the top of the Empire State Building, which, if you haven't heard of, is pretty tall. In fact, it is about 320 meters tall, assuming they go all the way to the top, which I guess they probably do. So if you wanted to see how much punishment that is, we're about to calculate it. So they say, how much gravitational potential energy would a 70 kilogram racer gain during this race? So here is it's a work equation, right? Work equals F delta X. All energy is probably based around the work equation. And for gravitational potential, that's an mg that you're working against. You're pushing against gravity, and it's a height for the delta X, which is the distance you go against gravity. So for us, we have a 70 kilogram racer is the mass. Gravity will be 9.8. And the height that we're going up is 320 meters, like so. So pretty straightforward problem. Let's see what my calculator has to say about it. 70 by 9.8 by 320. And I come out with a big number. Well, hey, let's do that. 219,520 joules. And this looks like a 2 sig fig problem. So we're going to round to that one, or 220,000 joules about. Now, if you want to do quick math, a quick estimation, 4 joules is a calorie, so if you could divide this by 4, running up the Empire State Building is about a little more than 50,000 calories. You say, "Wow, that's a lot of energy that person used," but it's not, because remember, the food energy that's printed on foods is actually in kilocalories. So if you divide this by 1,000. Running up the Empire State Building, which sounds like a daunting task, only is going to cost you 50 kilocalories, which they always do on food packaging with a capital C. 50 calories. It's half a bag of chips. That's all you need to run up the Empire State Building. Depressing, huh? So, to lose weight, you're going to want to change what you eat. Don't run up the Empire State Building more times. You get more calories from food. All right, here we go. Little tangent there. Ranking tasks. Love some ranking tasks. We've got 4 of these balls flying through the air, and 3 of them look like they are in motion, and 1 of them is not. And we are curious who has the most to the least gravitational potential energy. And it looks like 1 is moving the fastest. He has the longest arrow. It looks like 2 and 4 have the same speed. 3 does not have any speed, but you know what? That's a distractor, because speed has nothing to do with gravitational potential energy in terms of calculating it. Not until we get to conservation. So all we care about is, at this instant, how much mgh do they have? That's gravitational potential, and this is the only thing different about them. They all have the same mass, they're all under the same gravity. So don't worry about m and g, just care about h. Who's got the most h? 3. 2 and 4, same height. 1, 0 height. So we're going to say that 3 comes first, followed by 2, which is equal to 4, followed by 1. That was a lot easier than maybe it looked. All right, let's talk some springs. You have this little tendon in the back of your heel, the Achilles tendon, and apparently this is what stores a lot of energy when you run, because if you stretch it, it's going to gain some energy, and you can use that stored stretch energy, elastic energy, to push off with. So we have this lady who's running, and we've graphed her force versus distance down here, or at least for that heel. this is the force that is used by her heel per distance stretch. Now, what energy is stored for this stretch when she reaches a maximum of 0.5 centimeter? Well, what we can get, here's what I'm going to do with this graph. Come on, there we go. We know for stored energy in a spring, the work equation tells us that it's going to be half of the stiffness of the spring times the x squared. Well, the spring in this case is her Achilles tendon. So we would need the K value of her Achilles tendon to finish this problem. Well, look what we've got. We've got an x here and a force here, and we need a K. So force equals kx, right? That's Hooke's law. So if we divide by x on both sides, that's a slope equation. That's a delta y over delta x equation equal to the slope. So k should be the slope of this particular graph. So let me go ahead and say that that point is 400 and 0.24, and this point is 0, 0. That makes that easy. I'm just going to do 400 divided by 0.24. Does that reduce easily? They do both divide by 4. That's going to give me 100 over 0.06. No, that's not too easy. I'll go ahead and put that in the calculator. 400 divided by 0.24. Okay, and I get a K value equal to 16666. It just keeps going like this. So let's plug that in here. The energy, which we could also call the elastic potential energy, at the maximum stretch of 50 centimeters will be half. Interesting. I did my K value in centimeters. So I think I better put my X in centimeters. Oh gosh, this is always tricky. No, I think I better change it to meters. So I'm going to change my, if I make this meters, so the 0.24 centimeters is going to be 0.0024 meters, and that would be newtons. So I actually have to move my decimal twice. So I'm going to get 16666 times, and then my x squared value here is in centimeters, so I'm going to change it to meters. It was 0.5 centimeters, so it's going to be 0.005 meters, and I'm squaring that. Okay, that should make sure that all my units are in the right place. So this was newtons per meter. And I'm doing that because newtons is already in meters, so I don't want to screw with that. It might have worked out if I did centimeters, but I'm just paranoid. All right, so let's do this in the calculator. Divide by 2 times 0.005 times 0.005. Okay. Oh, interesting. That's not a lot. Let me check and see if that's right. That is right. 2.083 repeated joules. And again, we're looking at basically a 2 sig fig problem. So we're going to round to there. That's confusing because I wrote the repeated bar here, but that's not what I wanted to do for sig figs. So let's go ahead and change that to 2.1 joules of energy is stored in her Achilles tendon, which compared to the weight of a human body is not that much. That's all right. You get a little extra energy from it. Do I have any more? Yep. Here it is. When a spring is stretched by 5 centimeters, its elastic potential energy is a joule. What will its elastic potential energy be if it is compressed by 10 centimeters? All right, we can do this as a proportionality, right? 1/2 kx squared is the work equation for a spring for elastic potential energy. When I compress it a distance, that's the x of 5, I get a joule back. What happens if I double that? Now, it doesn't matter that we're compressing it, because think, this is a squared value. Even if I get a negative distance, it will square out. So we don't care that this is being compressed instead of stretched. As long as it's a spring, we're good. So I go from 5 to 10. I'm doubling the stretch. Well, that means I'm going from 1/2 kx squared to 1/2 k of 2x squared. And when I square 2x, I get 1/2 k 4x squared, which I can factor the 4 out. I'm going backwards here, but that's fine. 4 times 1/2 kx squared. So when I double my x, I get a factor of 4 back. So if I started with 1 joule, now I should have a total of 4 joules. There you go. So that's a good, and that proportionality kind of thing is going to come up all the time on tests where they ask you, I double the stretch, or I double the radius, or I triple it. How much more do I get? Well, if it's a squared relationship, you get the square of how much if you doubled it, the square is 4. If you triple it, the square is 9. So there you go. All right, hope this was helpful to you in solving stored energy problems.